Okay, these are helpful homework hints on Math 114, homework number 5, the hand-in. And we have the volume of an ellipsoid given by this formula, 4/3 pi ABC, where the A, B, and C come from the generic equation for the ellipsoid. Now what's going to happen is A is going to be changing, and B is going to be changing, and C is going to be changing. So we first think about velocity as a function of A, B, and C. And then we could see at this setup, though, that we have those guys changing with time. A, B, and C are. So this will be then thinking about the function as a function of t. And we can discuss how the volume is changing with time using the chain rule. And so it's a chain rule related rates question where we have the take each of these variables A, B, and C and find partial derivatives, and then multiply those partial derivatives by the corresponding rate of change of A with t, and B with t, and C with t, and you get the formula for how volume is changing with time. And so that's what this question is really asking. The dA dt, dB dt, and dC dt are constants. In the formula, you'll have A, B, and C. When we do related rates, we're interested in a particular instant in time. The instant when A is 1, and B is 3, and C is 5. And so if your formula for the partial derivative of volume with respect to A, B, or C, if those involve A, B, and C, which they will, then you can plug in these given quantities here. And we know how dA dt, the rate of change of dA dt were given, the rate of change of dB dt were given, and they want us to find out, this is dC dt, they want us to find that in order for the volume to remain constant, and remaining constant is just having a change with respect to time. This guy here must then be 0. So find dC dt if VD dt must be 0. That's what this question is asking. Okay? Alright, great. This next question here, we have z is a surface, and it's given to you as a function of x and y explicitly. And they're asking about the tangent plane. And you have two options. We have z minus z naught is this formula here. This is when you're given an explicit formula like what we have. Z is a function of x and y. You use this one. But you could also use this one. This is more often used when you have w as some function of x, y, and z, generally when it is an implicit formula. And so we saw this in section 14.5, and this in section 14.6, I think. And so, but if you do have it in this format here, like we do, then we could set it up to be in the other format by just subtracting the z over, or subtracting the function over. Either way, we could do w is f minus z, or we could do w is z minus f, one or the other. And so, say we choose the first one. The w is f minus z. That seems the most obvious thing to do. Just move the z over. And now you have this function w. When you go look at the difference between these two equations, they have the same initial parts to it then if you're looking at it in that format. And so the capital F here would be pretty much the little f minus z. And so the capital F of x, since z doesn't have any x's in it, that's going to be little f of x. And the capital F of y is going to be little f of y. These are going to be the same. Now here's where they differ at. The capital F of z is not involved in the one formula, but just think about what it is here. If you have this setup, then capital F of z is a negative 1. And so the coefficient on z would be a negative 1 in this setup. If you wanted the coefficient on z to be a positive 1, then you would go with this version of it. And so, now back to the problem. We're talking about some other plane. We want the tangent plane parallel to some other plane. Parallel planes have normals that are scalar multiples of each other. So the normal for that plane is 1, 4, 1. So my tangent plane, which I'm looking at two different versions of the equations, my tangent plane must be a scalar multiple of that. My tangent plane's normal vector must be a scalar multiple of this normal vector. Maybe the scalar multiple is 1. So maybe say my scalar, this is the tangent plane's normal vector v is some scalar multiple of the given plane's normal vector. So I call this guy n. Okay, but the tangent plane's normal vector is the gradient. On capital F, that is. And so, we can find out, well, what's the constant need to be? And so, V is the capital F sub x and capital F sub y and capital F sub z. But the way we have it set up here is the same as little fx and little fy. But the fz is different. It doesn't have it. It's not in the other one. I mean, what I mean by different, I mean it's known to be in this setup that we go with here. F sub z is a negative 1. And then this is supposed to be set equal to some k times the given plane's normal vector, which is 1, 4, 1. We can figure out what the constant k must be then. Because based on the third component, two vectors are equal when they're equal component-wise, and so the third component will tell us then that that minus 1 is k times 1, so it tells us what the scalar multiple is, in this case, negative 1. If you set it up this way, if we had set it up the other way, then the scalar multiple would be exactly 1. But here we go, k is negative 1. So then we can take these partials here and set them equal to k times 1 and k times 4. So fx should be equal to k times 1, or negative 1, and this is not just any fx, this is fx at our point, x naught, y naught. Officially the z naught doesn't play a role. And then fy should be k times 4, which is going to be negative 4. So take these partials and set the one equal to negative 1 and the other equal to negative 4, and then you'll have equations for x naught and y naught. Take those back into the original function to find out then what z naught is. That's my advice for that question. So fx is going to be little fx, which is 2x plus 1, and fy is going to be little fy, which is just 4y. And you're going to set these equal to -1 and -4 respectively when you evaluate them at x0 and y0. So we can say at x0, y0. So we'll solve for x0, y0. I'll let you finish it out. And then you'll go back into the original function and find z0.